Hello, my name is Carter. This is step 1 at 1994, question 4 on theme of integration. I just clocked. I don't have my iPad. Give me 2 seconds. I always do this. I just like start the video and I don't even have my iPad, guys. Hold on, bear with me. Okay, so this question's on the theme of integration. All right, so we need to show first of all, well, integration, but also there's a little bit of trig at the beginning. So we need to first show that 1 minus cosine alpha over sine alpha is equal to tan of alpha over 2. So how are we going to do this? Well, first of all, we need to figure out, well, what's 1 minus cosine alpha? Well, in general, we know that cosine 2 alpha, it's a good place to start, is equal to 1 minus 2 sine squared alpha. Okay, this is just a double angle formula that you should know from A level. And what you can do is you can be a little bit strategic. You can take alpha and bring it to alpha over 2. So if alpha was like 8, you could bring it to 4, right? And that's fine because like this identity is still the same. It's just you're changing the alpha, you're making it alpha over 2. You're just halving like the thing that you're inputting, or part of the thing that you're inputting. So all in all, what you get then is 2 times alpha over 2 is equal to 1 minus 2 sine squared alpha over 2, right? Which effectively gives you cosine alpha in terms of sine alpha. So then you can get cosine alpha is 1 minus 2 sine squared alpha over 2, right? And that means rearranging this, you can see therefore that 2 sine squared alpha over 2 is equal to 1 minus cosine alpha, right? Similarly, we can, since we looked at cosine 2 alpha here, you might as well also look at sine 2 alpha. So obviously sine 2 alpha is equal to 2 sine alpha cosine alpha, right? And again, we can do the same trick, bring alpha to alpha over 2. And this gives us sine of 2 times alpha over 2, which is alpha, is simply equal to 2 sine alpha over 2 cosine alpha over 2. Okay, so now what we can do is we can consider 1 minus cosine alpha over sine alpha, which is simply just 2 sine squared alpha, 2 sine squared alpha over 2, divided by 2 sine alpha over 2 cosine alpha over 2. So obviously the 2's cancel out, one of the sines cancel out, and the cosine stays the same. This just gives you sine of alpha over 2 divided by cosine of alpha over 2, which is clearly just going to be tan of alpha over 2. Sine x over cos x is tan x, as required. Okay, so that's the first part of the question. Really nothing there that I would think is too tricky. But the second part of the question is really, I think, probably the trickier part. Okay, so what are we going to do? Well, we're going to let, effectively, if I go down, we're going to let I be some integral that we want to calculate. So for this question, it's the integral of dx over 1 minus 2kx add x squared. And we're given the constraint that the mod of k I assume is a real number, the mod of k is less than 1, right? So effectively, for some real number k, its mod is less than 1. So it's like between minus 1 and 1, effectively, right? This is just the same thing as me saying minus 1 is less than k is less than 1, right? Okay. And so effectively then, what I can do is I can complete the square on the denominator. So if I look at my denominator, I have 1 minus 2kx plus x squared, which is effectively the same thing as x squared minus 2kx add 1. That's how I like to put my quadratic in, like that's the form I put my quadratic into before I complete the square. When I complete the square on this, obviously what I'm going to get is x minus k squared plus 1. So add 1 minus k squared. So that's my completed square, whatever. And effectively this just therefore gives me the integral of dx over, what's it going to be, x minus k all squared, add 1 minus k squared, okay? And then what we can do is we can define a, so I'm going to let lowercase a equal the square root of 1 minus k squared. And we will obviously the square root of any like real number of really, well, it's really only defined for positive real inputs, right? So if the square root of any number is going to be greater than 0, but for that to happen, this needs to be a positive real. So 1 minus k squared also needs to be greater than 0, right? And so effectively, we get that 1 is greater than k squared is less than 1. Take square roots of both sides, so the mod of k is less than 1. So you can see where that condition is coming from, simply because the reason why, well, to be fair, the solution had the mod of k less than 1. I just introduced it arbitrarily there. But that's the reason why they're saying if the mod of k is less than 1, right? Because if the mod of k is less than 1, then we're allowed to effectively introduce it here. So now I'm realizing actually the solution didn't have this. This is a condition that we did have, so I was correct. Mod k less than 1 is a condition we're given, but the reason why that condition is good is because it allows us to make this substitution. A is equal to the square root of 1 minus k squared. And obviously that's going to be greater than 0. We're taking the real value of k between minus 1 and 1. Okay, very cool. So then what we can do is we can write this integral here as dx over the integral of dx over x minus k all squared add a squared, right? And now we can follow this up with a substitution. Let u equal, let me just also move this. Let u equal x minus k. Clearly, du dx is equal to 1, so du is equal to dx, right? And so ultimately what we get from this is we get that I is equal to the integral of du over u squared add a squared. Now this is, some people know this integral off by heart, but I'll go through it. Effectively, you can let u equal aw, right? So du dw is equal to a, so du is equal to a dw. And so therefore what we have, our integral becomes the integral of a dw divided by a squared w squared add a squared. So we can factor out the a squared from the denominator. So this gives me a, well, actually, first of all, we can divide top and bottom by a, so you're just going to get dw over aw plus a, the integral of that, which is equal to the integral of dw over a multiplied by w plus 1, which is simply just 1 over a multiplied by the, sorry, w squared. So obviously it's going to be 1 over a multiplied by the integral of dw over w squared plus 1. This is just arctan of w. That I'm going to assume you know. So effectively this is just going to be 1 over a arctan of w. So arctan of w. Now remembering, obviously w is equal to, well, u is equal to wa. So w is equal to u over a. So we can just reintroduce that. So obviously this is also going to be plus c since we have an indefinite integral. So this just gives us 1 over a arctan of u over a plus c. And then from here, we remember what a is. A is equal to the square root of 1 minus k squared, if I'm thinking correctly. And then u, obviously, we also made that as a substitution. We set u equal to x minus k. So we have that. We can just replace the u here with the x minus k, and the a with the square root of 1 minus k squared. And then we're done. And obviously, this is with the condition that mod of k is less than 1. So all in all, the integral that we set out to solve is just equivalent to 1 over the square root of 1 minus k squared, arctan of x minus k all over the square root of 1 minus k squared, plus a constant of integration, all under the condition that the mod of k is less than 1. K is, I assume, some real number between -1 and 1. So that square root is a real number. Okay. A positive real number if you want to be specific. Okay, right, so is that exactly what they have? I hope it is. So 1 over the square root of 1 minus k squared arctan of x minus k all over the square root of 1 minus k squared plus c, where c is constant integration. Okay, hence or otherwise show that if 0 is less than alpha is less than pi, then this definite integral is equal to pi minus alpha. Did I say a? I mean alpha. If 0 is less than alpha is less than pi, then the integral, this definite integral is equal to pi minus alpha over 2. Okay? Alright, let's just get straight into it then. Well, immediately, if we just have a look at the indefinite form of that integral, then what we're going to have is we're going to have indefinitely the integral of sine alpha dx over 1 minus 2x cosine alpha add x squared dx. Now, if I just, obviously sine alpha has nothing to do with x, it's a constant with respect to x, so we can put it out the integral. Sine alpha integral dx over 1 minus 2x cosine alpha plus x squared. Now, if we go back up, effectively, to the integral that we were just solving, it's 1 minus 2kx plus x squared, and on the denominator, and a dx on the top. Well, this is how we have our dx on the top, 1 minus 2x cosine alpha plus x squared. So effectively, you can see here, this is just the same as the integral we just solved, but with k is equal to cosine alpha. So we know the answer. We don't need to do any no dilly-dallying. We can just go straight into it. Sine alpha multiplied by 1 over the square root of 1 minus k squared. K here is cosine alpha. So 1 minus cos squared alpha multiplied by arctan. This, I should actually be zooming out here, my bad. Multiplied by arctan of x minus sine alpha. Oh, sorry, cosine alpha is our k here, isn't it? So x minus cosine alpha over the square root of 1 minus cos squared alpha. Okay, now it should be known that cosine squared alpha and sine squared alpha is equal to 1. So 1 minus cosine squared alpha is equal to sine squared alpha. Square rooted is equal to, well, technically the mod of sine alpha, but I think we have 0 between alpha. So alpha is between 0 and pi, so sine is positive there anyway, so no need for mods. So effectively, we can just say this is equal to sine alpha multiplied by 1 over sine alpha arctan of x minus cosine alpha divided by sine alpha. Okay, and that and we can obviously get rid of these signs. Okay, so this just gives us arctan of x minus cosine alpha divided by sine alpha, and of course we'll have a constant of integration plus c. So this is going to be our indefinite integral, effectively our indefinite, the answer to our indefinite integral of sine alpha dx over 1 minus 2x cosine alpha plus x squared. Now we need to have it, like, now we want to calculate the definite integral of this between 0 and 1. So effectively we just need to, like, evaluate, effectively, well, let me just write it all out. So sine alpha dx over 1 minus 2x cosine alpha add x squared, right? I wrote an extra dx up here as well. My bad about that. I didn't mean to write an extra dx up there. That's my bad. Okay, so effectively we have this integral. Obviously, we already know what the answer is. So effectively, we need to evaluate it between 0 and 1. So the answer is arctan of x minus cosine alpha divided by sine alpha, right, between 0 and 1. Now, obviously, at 1, we're going to get arctan of 1 minus cosine alpha divided by sine alpha, and then minus, effectively, it's just how you evaluate definite integrals. You do effectively the answer, this is how you evaluate definite integrals, is you evaluate the indefinite integral at the sort of top limit, and then you subtract this sort of indefinite integral evaluated at the bottom limit. So effectively it's just going to be arctan of 1 minus cosine alpha over sine alpha minus, that should be arctan, minus arctan of 0, so just 0 minus cosine alpha, just minus cosine alpha divided by sine alpha. Okay, so this is our answer, but it's not quite in the form that we want it to be. So we have to recall that obviously 1 minus cosine alpha over sine alpha is equal to tan of alpha over 2. So then what we have in the first bracket is just arctan of tan of alpha over 2. Okay, and effectively, because we have tan being between 0 and, because we have alpha being between, so 0 is less than alpha is less than pi, alpha over 2 is between 0 and pi over 2, which is effectively part of the region where arctan, in this region, arctan of tan of that value is just going to be exactly equal to that value. And so effectively, arctan of tan of alpha over 2 is just going to be alpha over 2 here, right? And again, that's just effectively because whenever we have, so obviously our tan graph looks something like this, right? And so we define arctan of x between minus pi over 2 and pi over 2. And obviously this is tan of x, so arctan of x is an inverse function, so it's going to be reflected in the line y equals x. And so effectively, the thing that we require is that our y value of arctan of whatever that is between pi over 2 and minus pi over 2. And we're guaranteed for that to happen here, because effectively the thing that we're inputting here is exactly between 0 and pi over 2, right? So effectively, because I'm inputting here that something, my x value is between 0 and pi over 2, that just means, so it's actually in this region over here, and it means that, for example, if I just plug in like pi over 4, that's also going to be within like my, effectively, when I do arctan of that value, it's just going to bring me back to my pi over 4, because my arctan is defined between minus pi over 2 and pi over 2, and effectively my input here, pi over 4, when I plug that into tan, and then back into arctan, obviously the inverse functions, so I will just get pi over 4 back. However, if I had something on the outside here, like for example, this is going to be pi. If I have something over here, like, I don't know, like something to the right of pi, and then I do tan of that value in arctan, I'm not going to get this value, I'm going to get this value subtract pi. Okay, so that's the difference, right? Because effectively, my arctan is defined between minus pi over 2 and pi over 2. Whenever effectively I plug something into arctan, the thing I'm going to get out has to be between between minus pi over 2 and pi over 2, right? In this case, alpha over 2 is between minus pi over 2 and pi over 2. Specifically, it's between 0 and pi over 2. And so effectively what that means is that it's going to give me exactly alpha over 2. If my alpha over 2 was actually greater than pi, then it would map back to something between minus pi over 2 and pi over 2 when I plug it into the arctan. So that's effectively what I was trying to say. And so all in all, what we end up getting here, arctan of tan of alpha over 2, is simply just going to be alpha over 2, because the way that like alpha is defined, 0 is less than alpha is less than pi. Okay, so from that first thing we get arctan of 1 minus cosine alpha over sine alpha just ends up being exactly alpha over 2. However, arctan of minus cosine alpha over sine alpha is effectively the same thing as arctan of cot alpha, right? So, sorry, minus cot alpha. Since effectively cot alpha is 1 over tan alpha, and tan alpha is sine alpha over cosine alpha, so it just gives you cosine alpha over sine alpha, and we have a minus in front. Okay, now, there's actually a relationship between tan and cot, which is quite important. Effectively, it just tells you that cot alpha is equal to tan of pi over 2 minus alpha. Okay, and effectively, the way that we can see this, one of the ways that we can see this, is effectively by looking at their graph. So let me see if I can try and get this up. So Desmos, if we just look, so tan of pi over 2 minus alpha, right? If you just take tan of alpha, tan of minus alpha is effectively going to be a reflection in the y-axis, right? So if I just take tan of x, tan of minus x, you'll see is going to be a reflection. So does it work? Tan of minus x is just clearly a reflection of tan x in the y-axis. Then obviously from that you're going to add pi over 2. So you're going to shift it to the left by pi over 2, right? You're doing that plus pi over 2. So this plus pi over 2. So you've shifted it to the left by a factor of pi over 2. And if you think about it carefully, we have tan x and we have tan of minus x plus pi over 2. This clearly is actually just cotangent of x, right? It's not a really rigorous proof, but you can see it, right? Because clearly cotangent of x is 1 over tangent of x, or 1 over tan x. 1 over 0 is going to blow up to infinity, so that makes sense why that's happening here. Obviously, we also have here pi over 2, 0. So here, it's normally at pi over 2, tan blows to infinity, so 1 over infinity is practically 0, effectively, informally anyway. And then here we have pi over 4. Tan of pi over 4 is 1. 1 over pi over 4, 1 is just 1. So this makes sense. And if we actually graph cot x, it actually, you can see the green coincides with the blue, so they're the same. So that's one way of seeing that those two graphs are actually the same. And it's a useful identity in general to just have, like, in your bank of identities. Okay. So because we know that, then we effectively have that arctan of minus cot alpha is effectively just the same as arctan of minus tan of pi over 2 minus alpha. Right? Now, we still have this minus sign here, which is a bit annoying, because otherwise you'd just be able to say arctan of tan or something, just inverse. But that's okay, because tan is an odd function, which means tan of minus x is equal to minus tan x. Okay, so effectively what this means is that it's symmetric about the origin. Okay, in other words, when you effectively flip it by the when you reflect tan x on the y-axis, it's the same as if you reflected it in the x-axis. So let's just have a look at this. So obviously tan of minus x we already saw before. Tan of minus x. Don't want to do x tan minus x. I want to do tan of minus x, and you can see minus tan x here. Right, effectively it's the exact same. And if I look at tan x, right, effectively what that means is that me reflecting it in the y-axis is the same as me reflecting it in the x-axis. So it's symmetric, we say, about the origin. Okay, so that's just a property of tan. So tan of minus x is actually equal to minus tan x, right? And you can see that because the purple and the red are coinciding. Okay, so we can use that property here and just bring the minus sign inside to tan. Okay, and so this just gives you is equal to arctan of minus pi over 2 minus alpha, like this. So we have a lot of brackets going on here, but obviously we can use the same trick as before. Arctan of minus pi over 2 minus alpha is just the same as arctan of alpha minus pi over 2. Now obviously alpha is between 0 and pi over 2, and pi. So alpha minus pi over 2 is going to be between minus pi over 2 and pi over 2, right? Alpha minus pi over 2 here. Okay, and that's perfectly fine, right? Remember, because we have tan of that value, right? And arctan effectively effectively will always just output a value between minus pi over 2 and pi over 2, we're guaranteed that we're going to get this exact output back, alpha minus pi over 2. Because it's between minus pi over 2 and pi over 2, then we know that arctan of tan of alpha minus pi over 2 is just going to be alpha minus pi over 2. If this was, for example, greater than pi, then again we would have that problem with our tan, right, where it's greater than pi, so it's lying like somewhere over here, right? And effectively it has to be mapped back to the sort of principal domain or principal range, I guess, because the domain of tan x is into the range of arctan x, right? So effectively it's going to be just sort of sent back to the sort of principal domain where we define arctan of x, right? And so that's just the reason why it's actually good to have alpha between 0 and pi here. Okay, so that just gives you alpha minus pi over 2, and now all we need to do is just combine these, right? So effectively, we had arctan of 1 minus cosine alpha over sine alpha, which we showed is alpha over 2, minus arctan of minus cosine alpha over sine alpha, which we showed is alpha minus pi over 2. So when we just subtract those two things, alpha over 2 minus alpha, so let me just go back up, alpha over 2 minus alpha is simply going to be minus alpha over 2, and then add pi over 2, sorry, because the minus cancel. So this just gives you pi over 2 minus alpha over 2, which is simply pi minus alpha over 2, which is the answer that we sought to get. So, very, very, very interesting question. A few intricacies in there that could like bog you down if you sort of think about them for too long, such as the mod of k being less than 1. It's kind of like, why is that there? And also this sort of range 0 less than alpha less than pi. But if you disregard those things and you just sort of do the maths, it actually ends up being okay anyway. They're not intricacies that really bog the question down too much. You could do the question without them. But effectively, they're just there to be precise about the maths and be like, we're 100% certain that like this is true only when this is true, right? So we include them for completion, but they don't actually bog down the question. It's more that you could just get confused because of those conditions, which could bog you down as a student. But I'm saying in this case, it actually wouldn't matter even if you didn't. So yeah, cool. Thank you guys for watching. I'll see you guys in the next one.